So let's carry on. So we want to show that minus f is Riemann integrable and that the value of its integral is minus the integral of f. So if minus f is going to be Riemann integrable over the interval ab, then by our definition that means that we need to show the supremum over all dissections of the lower Riemann sums of, that should be minus f, not f, of minus f is equal to the infimum over all dissections of the upper Riemann sums of minus f. So, and then of course if this is the case, then the value of these two things will be equal to the integral of minus f dx over the interval ab. So to go further then, what we need to think about is what is the upper Riemann sum over a dissection of minus f and what is the lower Riemann sum over a dissection of minus f. And it's interesting. It's not as simple as you would think. It's not just equal to minus the upper Riemann sum of f. Like up here, where it's switched, there's going to be a switch here as well. So let's have a look at that. So if we think about the upper Riemann sum over a dissection of minus f, again, our dissection D could be any dissection, and for the sake of writing down what the sum is equal to, let's say it's splitting the interval AB up into n pieces. So by definition, this is the sum from I is equal to 1 to n of xi minus 1 of the supremum of the value of minus f. Now, the value of minus f is of course equal to just minus f. So by this definition here, we'll substitute in, instead of putting minus f of x, we're just putting in minus 1 times f of x. So this is minus f of x here, where x is allowed to vary over that interval xi minus 1 to xi. Now, we're going to use our result here. It's this result that we're going to use, but let me just convince you that we can do this. So our set x, if you like, is the set of all f of x values where x is allowed to vary over that interval xi minus 1 to xi. Our set minus x is therefore the set of all of the things in x times minus 1, so it's all the things of the form minus f of x, where x is allowed to vary over that interval xi minus 1 to xi. Now, this notation here just means the supremum of this set minus x here, and by the result here, that will be minus the infimum of this set. But we could write that infimum of this set another way. We could write it as the infimum, where x is allowed to vary over this, of f of x. So let's do that. So we can pull the, well actually we'll do it in a few more steps. We'll split it into two steps so it's obvious. Sum from I is equal to 1 to n of xi minus 1. And now we're going to have times minus 1 times the infimum. X is allowed to vary over xi minus 1 to xi of f of x. So let's just check that I've done that correctly. So we had the supremum of minus f of x, where x is allowed to vary over this, so it was the supremum of this set. By this result here, it's minus the infimum of that set x. So then we've just converted that back into this notation, so it's the infimum where x is allowed to vary over this of f of x. So yes, that's all fine. Now, that change, you could have done that for any of these intervals. There was nothing, I hadn't picked the specific one of the cut up intervals that we have here, so it applies for all of them. So we can pull this minus 1 out the front, and then of course the thing we're going to be left with, if you get rid of this, that's just the lower Riemann sum of the function f for our dissection D. So this is actually going to be equal to minus the lower Riemann sum over the dissection D for our function f. So that's our overall result then, that the upper Riemann sum over any dissection of minus f is equal to minus the lower Riemann sum over that dissection for the original function f. So yes, it's switched round in this way. Just like up here, where the supremum of negative x wasn't just minus the supremum of x, instead it was minus the infimum, so you had to switch round from supremum to infimum here, and here likewise you had to switch from infimum to supremum. Here you've switched as well, it's not just minus the upper Riemann sum of f, instead it's minus the lower Riemann sum, and of course the same thing is going to happen for the lower Riemann sum, so let's do that next. So if we consider the lower Riemann sum over our dissection D of minus f, by definition that is the sum from I is equal to 1 to n of xi minus 1 times the infimum of the values of minus f of x, but of course that's just minus f of x, where x is allowed to vary over xi minus 1 to xi. Now, our sets here are exactly the same, so when we've got this infimum here, this is actually just the infimum of this set negative x up here, which by our result up here is equal to minus the supremum of the set x. Now let's translate that back into our other notation. So this is going to be the sum from I is equal to 1 to n of xi minus 1 times again minus 1, and then it's going to be times the supremum of the values of f of x, where x is allowed to vary over xi minus 1 to xi, because the values of f of x, where x is allowed to vary over this, those are the elements of that set x. So that's all nice. And of course, this didn't just apply to one of the cut up bits of the interval that we've got, it applies to all of them, so you can do it for every single one of them. You can pull that minus one out the front, but then of course if you get rid of the minus there, this is then just the definition of the upper Riemann sum over the dissection D for our function f. So this is therefore going to be minus the upper Riemann sum over the dissection D of f. So those are the overall two results that we've got. The upper Riemann sum for our function minus f over some dissection is equal to the is equal to minus. The minus is very important. It's not just equal to the lower Riemann sum. Is equal to minus the lower Riemann sum over that dissection of f, and the lower Riemann sum over that dissection of minus f is equal to minus the upper Riemann sum over that dissection of the original function f. So what we're going to do next is we're going to take these two expressions that we've derived and we're going to use them up here. So remember, our aim is to show that this is equal to this, so the supremum of the lower Riemann sums is equal to the infimum of the upper Riemann sums. We're now going to replace the lower Riemann sum of negative f and the upper Riemann sum of negative f with the expressions that we've got. And we're going to see if from that we're able to show that these two are equal to one another using the fact that the function f is Riemann integrable. So let's start with the infimum of the upper Riemann sums. So the infimum over all dissections of the upper Riemann sums of negative f. So again, remember that this is just notation. Really what this means is the infimum of the set of all possible upper Riemann sums where you vary the dissection. So you're allowed to use whatever dissection you like of this interval AB. So take every possible dissection. Again, it's an incredibly complicated set. Put all those upper Riemann sums into a great big set and take the infimum of that. That's what this notation really means. Now, for every single one of those upper Riemann sums, we now know that we can replace that with minus the lower Riemann sum over the same dissection of the function f. So that means that this is the same thing as the infimum of this set of minus the lower Riemann sum over the dissection D of the function f. Now, what we can do is apply our rules here, because this set is minus another set. So our set x this time is the set of all lower Riemann sums of the function f, where you vary over every single dissection, and this set is then negative of that set. So we're taking the infimum of minus this x, which using this one here, we can say is minus the supremum of the set x. So this is equal to this is equal to this is now equal to minus the supremum of the set x, which is the set of all lower Riemann sums, where you're allowed to go over every single dissection. But of course that has another way of writing it, the supremum over all dissections of the lower Riemann sums of f. So this thing here is now equal to minus the supremum over all dissections of the lower Riemann sums of f. And because f is Riemann integrable, we know what this is equal to. This is just equal to the integral of f over the interval ab. So let's, in fact, I'll write that final step. This is equal to minus the integral of f dx over ab, because of the fact that f is Riemann integrable. So this is equal to the infimum of the upper Riemann sums of f, and they're both equal to this value. So keeping the minus sign there, we've got minus this. So this all looks to be going rather well. All we now need to show is that this other one, the supremum of the lower Riemann sums of negative f, is also equal to this, and we'll be done. We'll then have that both of them are equal to one another, and they're both equal to this value, which is exactly what we wanted to show. So exactly the same strategy, the supremum over all dissections then of the lower Riemann sums of minus f. Again, this is a great big set. We can write it out in full. So it's really the supremum of the set of all lower Riemann sums of minus f, where you're allowed to use whichever dissection you like. And now what we can do is say that every single one of these we can rewrite it's equal to minus the upper Riemann sum over that same dissection of f. So this is equal to minus the upper Riemann sum over that dissection of f. So this as a set is therefore equal to the set of all minus upper Riemann sums of the function f, where you vary over every single dissection. So the supremum of it will equal the supremum of this. So this is now equal to this. And now, of course, we're going to use one of our facts about suprema now. So we can consider now the set x is equal to the set of all upper Riemann sums of the function f over all dissections. So this, therefore, is equal to minus that set x. So we're taking the supremum of minus x, which is equal to minus the infimum of x. So this is therefore equal to minus the infimum of this set x, which is the set of all upper Riemann sums of the function f, where you vary over all dissections. And then again, because the function f is Riemann integrable, this value is equal to the value of the integral of f over the interval ab. So this is therefore equal to, well, this same thing. I don't really even need to write it out again. I can just extend the equals here. So to summarize then, we have shown that for our function minus f, the supremum of the lower Riemann sums and the infimum of the upper Riemann sums are equal to one another. Therefore, minus f is Riemann integrable over this interval ab. And the value of that integral, is the value of these two things, which is equal to minus the integral of f over the interval ab. So that's part 2 of our proof of linearity complete. We now just have part 3, which is unfortunately the most difficult bit, and we'll do that in the next section.